Root mean square error. In the lectures till this point, we mainly used sum of squares error as the error function. So first of all, why do we need an error function? Error function. The requirement is that if we are building a model, during training phase, we need to have some sort of a measurement, an estimation of how good a model is at this point so that we can make improvements on the model. That is, let's say we are modeling one particular, let's say, regression or something. In that case, our main aim is to minimize the error. So we need an error term so that we can understand. We need to choose the coefficients such that our error is minimized. So as we discussed earlier, what is the error term in that? Let us say we have sum of squares error. We were considering sum of squares error sum of squares. What was the error in that? It is sum of square of what? That is the error term. Error term, we said it was the difference between the observation and the target. Our observation was y of xw and a target we had called it t. The difference between them, that was a error term. So where did this y come from? Initially we had data which had details of x and t, which said for this particular value of x, this is the target t. This particular value of x, this is the target t. This was the initial data provided. Using this data, we wanted to make a model which would learn how to predict the values of t. How did we do that? Let's take linear regression case that we already learned. In that case, we modeled it like y of xw is equal to, let's say there is only one x term, w0 plus w1x. So here y is the value that we found out using our linear regression and t is the actual target. So what will you do? You will first take one value of x. For that value of x, you will find the value of y. Then in order to find the error term, you will check the difference between the value of y that you found and the actual value of t. So that difference between the value of y that you found and the actual value of t, that is the error term here, y of xw minus t, right? So now let us start with the sum of squares error and we'll see how root mean square error is different from sum of squares error. So in sum of squares error, the name itself says it is the sum of squares of the error terms. So I'll remove this off. Sum is the sum of, let us say there are n different data points, then sum from n is equal to 1 to n of all the n data points, square of what? What thing is we going to square? The error term. Error term is the difference between y and our target. That is y of x n w minus what is our target? T n, right? This square. So this is a sum of squares. So what will this do? For n data points, we have n data points. For each of the point, it will find the error. Then it will take the sum of squares. First, it will square the term and then it will take the sum. Why are we squaring here? There are two reasons. The first reason is that, as we previously discussed, first reason is that we want to always have a positive error. We don't want a negative error. So this y minus t, it can be positive or negative. When you square it, it will always be a positive term. Second thing is, we always want to penalize larger terms. The larger error always need to be penalized. That is penalized more. In order to penalize the larger term more, we are taking square. Now let's see what is root mean square error. Error root mean square, RMS. Okay. What is the difference between sum of square and root mean square? So we are considering this sum of square error as the base, and from that you will do root mean square, RMS. So as the name says, first thing is root mean and square. So first of all, this is the squared error that you already have. So I'll call it ESOS. So ESOS, that is sum of square of W. you have to take the mean of it. How do you take the mean? Mean is average. You totally have n different data points. So if you divide this by n, you get average. Average value. You first did the sum of squares. Now you are taking average. Average is mean. So in RMS, you already squared. Now you took mean. What is the next step? You have to find the root. So put a square root. This is RMS error, that is root mean square error. So squaring is what you did in sum of squares error. So you are taking that sum of squares error and substituting here. Then you took the mean by dividing by the total number of data points. And once you took the mean, you took the square root, that is root. This is the root mean square error. Let's see what are the advantages that you will get if you use root mean square error over sum of squares error. That is, and what situation should you prefer root mean square error, right? So whenever you learn a concept, it is important that you understand why this particular concept is important, and practically under what circumstances, what situations should you use this particular concept. If you know that, then your learning is worth it. So we'll see when to use root mean square error. What is the requirement? So the first advantage of using root mean square error is, let us say you are comparing different data sets. In that case, let us say you have a model and you want to compare the efficacy of this model on different data sets. If you use root mean square error, you get this particular advantage, that it is scale independent. Scale independent. Why it is scale independent? Because here you can have different types of data sets, but here you are dividing the whole value by n, which means if you have 10,000 different points in one data set and say only 1,000 different points in the second data sets, if you are using sum of squares error, most probably, or more than 99% cases, you will have this value as much higher than this value, because here you are only taking sum of 1,000 terms. Here you are summing up 10,000 terms, which means even if your first data set is closely fitting your model, still this will give a higher error, because here you have more number of data points. So basically your sum terms are increasing, which means your error will increase. And here, even if this fits poorly, still you will have a lower error because you have lesser number of terms to sum. But what happens if it is RMS error? Here you are anyway dividing by the total number of data points. So you will take this SOS error, sum of squares error, you will divide it by 10,000 in first case, which means it is scale independent. Irrespective of the number of data points, you will be able to easily compare between different sets of data sets which are having varying number of data points. This is the first advantage. That is, now you understood, right? Practically what to use if you want to compare data sets on the same model where you have data sets with different amount of data, this will be a good measure. Next thing is interpretability. Why is interpretability increasing? Interpretability. Why does this offer better interpretability? The reason is, here in the sum of squares model, you are squaring the terms and then taking sum. So let us say your target value t has values like 20, 21, 19 and so on. Let us say this is the target value. If you are taking sum of squares error, your error term will be magnified. But if you are taking RMS, then you are taking square root of the square, which means ultimately the value of this error is comparable to the value of t. So if your RMS error is, let's say, somewhere close to 1, so you can have a logical understanding that if the average value of my target t is 20, my model is having an error of around 1, which means my value will be somewhere around 19 to 21, most probably. So you can have this estimation that is 5% is what my model is erroring. This sort of an idea you will be getting. This is interpretability. So using RMS error, you have the advantages of making it scale independent and keeping it more interpretable.